Welcome to the deep dive. So, when you think about vitamin C in cancer, you probably picture it mostly as a shield, right? Protecting our DNA from damage.
Yeah, that's the common understanding. Definitely part of the picture.
But what if recent research is pointing to something maybe even more surprising?
Okay.
Like, what if tumors are actually, rejecting vitamin C?
Rejecting it.
Yeah. And what if having low levels of this vitamin inside the tumor is linked to it being, well, more aggressive and maybe harder to treat?
Wow, okay. That is counterintuitive. And it's not just theory, you're saying.
Seems not. That finding is really the jumping off point for our deep dive today.
Right. And we're looking at some specific sources here, including a study I saw in cancer research. It digs right into this.
Focusing on endometrial cancer, I think.
Exactly. Yeah. Endometrial cancer.
So our mission today is to sort of unpack all this, pull out the key insights, the surprising bits, and really help you understand what might be going on with vitamin C at, a deeper level.
Sounds good. Let's start with that core finding then, the surprising one.
Okay. So this research, Dr. Marguerite Vissers and her team in New Zealand.
Yep. University of Otago. That's the one. Their paper made a pretty stark observation.
Which was?
When they looked at these endometrial tumors, they found the tumor tissue itself consistently took up significantly less vitamin C than the healthy tissue right next to it.
Less? Okay, hang on. That feels completely backward. If vitamin C is supposed to be good, shouldn't the bad cells want less of it?
Oh.
Or, wait, no, shouldn't they soak it up if they need it? I'm confused.
It's confusing at first glance. It seems backward. But here's where it gets really interesting.
Okay.
They didn't just see less vitamin C. They found a clear correlation. The lower the concentration of vitamin C inside a tumor, the more aggressive that tumor seemed to be.
Okay.
So low vitamin C seemed to track with tumors that were better at surviving, growing faster.
And resisting treatment.
And often more resistant to therapy, exactly. It suggests the cancer cells aren't just passively low on vitamin C. It's almost like they're actively avoiding it or is being used up differently or kept out.
Okay, so low vitamin C in the tumor itself correlates with worse outcomes. Yeah. That's a powerful finding. But
Sure.
why? What's the link? How does low vitamin C actually help the tumor be more aggressive?
Right, the mechanism. This is where the deep dive gets into the molecular details.
Okay.
And it brings up a fascinating player, a protein called HIF1.
HIF1.
Okay, what's that?
It stands for hypoxia-inducible factor 1. Hypoxia just means low oxygen.
Right, and cancer cells often end up in low oxygen spots because they grow so fast, the blood supply can't keep up.
Exactly. So HIF1's main job, normally, is to help any cell survive when oxygen levels dip too low.
A survival switch, basically.
Kinda, yeah. Now, here's the next critical link the researchers found. Those tumors that were low in vitamin C, they consistently showed much higher levels of this HIF1 protein being active. So low C, high HIF1 activity, almost an inverse relationship inside the tumor.
Precisely. It looked like vitamin C levels were inversely tied to HIF1 activity.
And the sources talked about HIF1 having this sort of helper syndrome for cancer.
That's a good way to put it. HIF1 is meant to help any cell survive low oxygen. It doesn't check if the cell is healthy or cancerous.
So if a cancer cell is struggling for oxygen,
HIF1 steps in and helps it survive, too. It doesn't discriminate.
If you're enjoying this episode, don't forget to like, follow, or subscribe. It really helps support the podcast and lets me keep bringing you more content like this.
Okay, but how does it help the cancer cells specifically? What does it do?
A couple of really key things that basically fuel tumor growth. First, HIF1 helps the cancer cell change its metabolism.
How so?
It lets the cell convert sugar into energy without needing oxygen. Anaerobic respiration, essentially, keeps the lights on even when oxygen is scarce.
Got it. Powers the cell. What else?
Second, it promotes angiogenesis.
Growing new blood vessels.
Exactly. It signals for new blood vessels to grow around the tumor. Now, it's trying to bring more oxygen to the struggling tissue.
But in doing so, it actually builds the infrastructure the tumor needs to get bigger and even spread.
Precisely. The tumor gets the supply lines it needs.
So HIF1 helps the tumor get energy and build supply lines. And tumors actually, trigger this themselves?
Yes. This is the really cunning part. Tumors produce free radicals. We usually think of those in the context of antioxidants cleaning them up, right?
Yeah, general cell damage.
But in this specific pathway, these free radicals act like a signal. They activate HIF1.
No way. So the tumor makes the very things that flip the switch on its own helper protein.
Pretty much. By churning out these free radicals, the tumor basically ensures HIF-1 gets activated, creating the perfect conditions for its own aggressive growth.
Okay. Now, vitamin C has to come back in here somewhere. How does it break this cycle?
This is the elegance of this particular mechanism they uncovered. Vitamin C, being an antioxidant,
Right?
it intercepts and neutralizes those specific free radicals the tumor is making before they can get to HIF-1 and activate it.
Ah. So it's not just generic cleaning. It's specifically blocking the on signal for the tumor's critical survival switch, HIF-1.
You got it. That's the key. By preventing HIF-1 activation, vitamin C basically messes with the tumor's ability to use that oxygen-free energy pathway.
And limits the signal to build those new blood vessels.
Exactly. It helps to sort of starve the cancer cell of the support it needs, especially in those tough, low oxygen conditions.
Okay, now connecting it all back. The first finding makes total sense. Low vitamin C means more free radicals floating around.
Which means more HIF-1 gets activated.
This leads to a more aggressive tumor. Wow.
Right. And the implication there is pretty significant. If you could increase the vitamin C concentration inside the tumor.
You might reduce HIF-1 activity.
Potentially, yes. And that could make the tumor's environment less friendly, maybe limit its growth, maybe weaken it.
And maybe make it respond better to standard treatments.
That's the hope. Make it more susceptible to therapies. Dr. Vissers even suggested this mechanism might play a role in how vitamin C could potentially help prevent solid tumors from even forming.
It's really fascinating how this new research is adding the how to some much older ideas. You mentioned vitamin C in cancer. Linus Pauling comes to mind immediately.
Absolutely unavoidable comparison. Pauling, the double Nobel laureate, he was a huge proponent of high-dose vitamin C.
Controversial back then, though.
Very controversial. He claimed it could treat cancer, but the wider scientific community was skeptical, largely because the mechanism wasn't really understood.
But
now, decades later, research like this starts to provide a plausible scientific explanation for how vitamin C might actually exert some of those effects he talked about. It's validating some of those early ideas with molecular evidence.
So bringing it to today, based on these sources and findings, how is vitamin C actually being looked at or used now, especially thinking about dosage?
Well, for therapeutic use, aiming to impact mechanisms like this HIF-1 pathway, it's often about high-dose intravenous infusions, high-V vitamin C.
And high dose means?
We're not talking milligrams here, we're talking grams, like 7.5 grams, maybe 15, 30, 45 grams, sometimes even more per infusion. Big doses.
Okay. And what about just taking pills? Oral vitamin C.
Oral intake is usually discussed more for prevention or general health support. And honestly, the debate about the ideal daily oral dose is still very much alive.
Right. And the sources made an interesting point comparing us, humans, to other animals regarding vitamin C.
They did, and it's a pretty striking difference. Most animals think about dogs, goats, cats. Most mammals, really, they can make their own vitamin C inside their bodies.
We can't do that at all.
Nope. Humans, guinea pigs, and a few others, we lost that ability somewhere in evolution. We rely completely on our diet.
And those animals that make it, they make a lot.
They do, especially when they're sick or stressed. The sources mention figures like 20,000 milligrams a day, maybe even more, depending on the animal and the situation.
20,000 milligrams. Okay, that really puts our standard RDA's, recommended daily allowances in perspective. What are they, like 100 milligrams for an adult? Maybe 200 milligrams if you're stressed, according to some guidelines.
Exactly. It's a huge difference. And then you look at someone like Pauling, who reportedly took 18 grams, that's 18,000 milligrams daily.
And lived to 93, even with prostate cancer later in life.
It certainly makes you wonder if the amount needed just to prevent scurvy, the acute deficiency disease, is maybe very different from the amount that might be optimal for, say, resisting chronic diseases or supporting the body through major health challenges.
So diet is the first place to look then?
Absolutely. You can definitely boost your levels by focusing on fresh, whole foods. Fruits, vegetables, nuts, seeds, things that haven't been heavily processed. Processing often depletes vitamin C.
But sometimes diet isn't enough or needs change.
Right. That's where supplements can come in, maybe during times of high stress or if you feel like you're getting sick or during an illness.
And if someone is considering higher oral doses, anything to keep in mind.
Yeah, tolerance varies a lot between people. The most common sign you've taken too much at once is usually diarrhea, bowel tolerance, they call it.
So that's like a built-in signal to maybe back off or split the dose.
Exactly. Splitting a larger dose into smaller amounts throughout the day often helps with absorption and avoids that digestive upset.
Okay. But for those really high therapeutic doses, the thousands of milligrams you mentioned for infusions. Why infusions? Why not just eat like a crate of oranges?
Yeah, it really comes down to practicality and absorption limits. To get thousands, let alone tens of thousands of milligrams from food, you'd need to eat truly massive amounts, kilograms of fruit every day, or maybe 50 to 100 grams of something super concentrated like acerola powder. It's just not feasible.
And the body can only absorb so much orally at one time anyway, right?
Right. Phi infusion bypasses the digestive system limitations and gets a very high concentration directly into the bloodstream quickly. The doctor determines the right preparation and dose for that, of course.
Wow. This whole deep dive has really shifted my perspective on vitamin C. It's not just this generic shield anymore.
No, it seems it might have these very specific roles, like interfering with that HIF1 survival strategy tumors use.
That core finding tumors having less C, and that low level linking up with this HIF1 protein that helps them thrive, it provides such a concrete mechanism to think about.
Yeah, the idea that vitamin C could block the signal activating that helper protein, it's pretty compelling.
It really is promising. That research into something so, well, common, so accessible, could reveal these specific molecular pathways. It adds real scientific weight to its potential in cancer care, both prevention and maybe treatment support.
It definitely makes you think more about nutrition and our baseline needs, for sure.
Absolutely. Which actually leads perfectly to a final thought for you, the listener, to maybe chew on. Considering that we humans, unlike most animals, totally lack the ability to make any vitamin C ourselves. How do our current standard daily recommendations really stack up against what our bodies might actually need? Especially when we're facing challenges like illness. What might we need if we could produce it ourselves like those animals do?
What does that evolutionary quirk imply about how we might optimize our health? Maybe through diet, maybe through supplements?
Exactly. Something to think about.
If you're enjoying this episode, don't forget to like, follow, or subscribe. It really helps support the podcast and lets me keep bringing you more content like this.